So let's get looking into some nuclear reactions, which are written actually in a format you should be fairly familiar with. They're just like chemical reactions, but in a chemical reaction, of course, the atoms rearrange. In a nuclear reaction, the nuclei change. This is a very distinct difference from a chemical reaction. So let's look at a really basic nuclear reaction. Let's say we have hydrogen 1 coming together with hydrogen 2. In fact, this is a very basic reaction, one of the very millions of types of reactions that occur in a star, like in our sun. So I bet we can make a prediction as to what's going to be in the products on the right-hand side here. So let's look at maybe the top. Like, if you had to take a guess as to what the mass number of the single particle that's formed might be, if you had to guess, what do you think it might be? Yeah, I bet you guessed 3, right? Now, what about the atomic number? What do you think that's going to be? If you just had to take a guess, the single thing made, probably 2. Yes, right, good. All right, so real basic things. Now, of course, here's what's interesting, right? This is hydrogen, which has atomic number 1. Hydrogen has atomic number 1, but now we're making one single thing with atomic number 2. What is that? Oh, that's helium. We actually made something new. And of course, there's going to be some energy exchange as well. But that's what's different about a nuclear reaction versus a chemical reaction. In a nuclear reaction, we make new elements. This is transmutation of elements. The nuclei actually change. There's something new, made something completely new. But a lot of the rules and a lot of the terminology we use for chemical reactions, they're sort of at play as well. So on the left-hand side, we call these things reactants. So there may be one reactant, maybe multiple reactants, right? Put a dot, 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 because it might be more than 2, whatever it is. Anything on the left-hand side, those are the things reacting. We call them reactants. The arrow here means produces or yields or forms. And on the right-hand side, we call these products. It might be one product, might be 2 products, might be dot, 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 multiple products. And then we write this as capital Q. Q is going to be our symbol here for energy. Any exchange of energy is given Q. This is what's called the Q value of the reaction, whether energy is absorbed or emitted, whether there's a positive or negative amount. This symbol is capital Q. Now, there's certain rules we can use to balance out these reactions, just like when you balance out a chemical reaction. One of the rules is conservation of charge. And that's shown here by the bottom number. Since this is atomic number, which is number of protons, you intrinsically knew that if there's 1 here and 1 here and made 2, that's really balancing the charge. There's a conservation of charge. So think about this not just as the number of protons in the nucleus, but actually the charge on the nuclei of each of these objects. We also sort of balance out the top number. What was that? Well, that was mass number. Now, be real careful. Remember, this is mass number, not mass. Because in a nuclear reaction, the mass won't be constant. In fact, that's one of the interesting things, one of the weird things about nuclear physics, is that the mass does not remain constant. But mass number does. So the number of things in the nucleus, that's going to remain constant. 1 here plus 2 here makes 3 over here. Sometimes the particles used to balance this all out are some of the fundamental particles we're used to using, like protons, neutrons, electrons. So let's write those things out, what they would look like as if it were a letter diagram. So a proton would be listed as such, right? It has a charge of 1 and a mass number of 1 because it's in the nucleus. Now, immediately you notice is the exact same thing as hydrogen, which is what we were looking at just the other day. We were looking at the binding energy of forming a nucleus. Right? The mass of the proton is really just the mass of a hydrogen nucleus, because they really are the same thing. A proton is a hydrogen nucleus. And what about for a neutron? Why don't you go ahead and write down what the neutron will look like in the same system? What's the charge of a neutron? 0. What's the mass number? 1, right? Because it's in the nucleus, so it has a charge at 0. Again, consider the bottom left-hand number to be charged in this case. And the top is 1 because it is a thing in the nucleus. All right, go ahead and write down what it should be for an electron. Okay, so the lower left-hand number here is the charge. What's the charge of an electron? In elementary charges, it's -1. What should the mass number be? Right, 0, because it's not in the nucleus. Now, be very careful. Remember, mass number is not mass. I'm really trying to be very clear about that. Mass number is not mass. It's just telling you how many things are in the nucleus. An electron is clearly not in the nucleus, so it gets a 0 there. That does not mean it has 0 mass. It just means it's not in the nucleus. Now, we can start to categorize these different reactions by what's happening. Remember, there's always going to be an exchange of mass, I should say a difference of mass. And so one of the possibilities is, what if the mass of the reactants is larger than the mass of the products? Because that's something that could happen. So that means we start with a certain amount of mass in the reactants, and then when the products form, there's now less mass in the products. So the question is, where does that mass go? Well, if you've been following along with this, you now remember that mass becomes energy. This means that energy is released. There's going to be a positive amount of energy here, so the Q value is going to be a positive amount. We're always going to write capital Q on the right-hand side as if it were a product. This means that there's energy being given off. That's what a positive Q value means. So if you start with a certain amount of mass on this side, we have less mass here. That means that some of the mass is escaping the system as energy, often in the form of heat, but it could be other forms of energy as well. It could be the kinetic energy of the particles moving away from this reaction. The other possibility, of course, is what if it's reversed? What if you start with a certain amount of mass, and then that's less than the mass of the product? So if we start with a certain amount of mass here, we actually end up with more mass on the product side. How could that happen? How could we gain mass? Well, it happens if energy is absorbed into the system. Energy then is on the left-hand side, if you want to think of it like that, and that adds mass to the system. But since we always list energy on the right-hand side, this gives a negative Q value, right? If Q is on the right-hand side, and Q is a negative number, that's like putting the negative number over to the left-hand side as a positive number. That means we're putting energy into the system. Energy is absorbed into the system as mass, and so the products now have more mass than they started with. Now, there are names given to these two types of reactions, which those of you taking chemistry should be very familiar with. This first one here is energy being released, or energy leaving the system, energy exiting the system. Do you know what that's called? That's exothermic. Thermic refers to thermal energy or heat energy, and again, as I mentioned, the Q, the energy exchange, is often in the form of heat, although it doesn't have to be, but this is the generic term for it. Anytime a system loses energy, energy exits the system, we call this an exothermic reaction. In this, the energy is absorbed, or energy enters the reaction. This is called an endothermic reaction. Always remembered as energy exits, energy enters. In fact, the prefix endo, END, really is the same as the same root as enter, ENT. In Latin, it does change from one to the other. That's the general idea. Energy exiting the system, energy entering the system. And both of these deal with another conservation rule. This is the conservation of mass energy. We're so used to conservation of mass, right? The mass of the system doesn't change, or conservation of energy, the energy of the system doesn't change, but that's not really the case anymore. That's, again, one of these weird concepts in nuclear physics, is that mass and energy, remember, are sort of the same thing. They're actually one quantity, which we call mass energy. And we get from one to the other by E equals mc squared. Here, E is going to be Q, so we can write it as Q equals delta m c squared. When there's a difference in mass, which there almost always will be in a nuclear reaction, it is either gained or lost as energy being released or absorbed into the system.